Okay, let's work another example where we deal with a relation on A, and A is the same set we just considered in the previous example. A is the set 1, 2, 3, 4, and again we're going to represent R in the form of a directed graph. The difference between this problem and the last problem, though, is that the edges of this directed graph are going to be different. So again, we have elements 1, 2, 3, 4, and our directed graph is going to look like this. First of all, each element 1, 2, 3, and 4 are going to kind of have a self-loop onto themselves. Then we're also going to have some directed edges between 1 and 3 and some directed edges between 2 and 4. So this is what the relation R looks like for this specific example as a directed graph for the problem that we're going to work. And like before, one of the first things we want to do is let's go ahead and write down what the set R is. What is the relation R? And we can figure that out simply by looking at the directed graph. So we start off writing down the set. And again, I like to start with each node in turn. So if we go to the first node, 1, I ask myself, starting at 1, where can I end up? Well, since I have a self loop on 1, I can start at 1 and end up at 1. So the element 1, 1 is an element of R. Starting at 1, I can also go to 3. So 1, 3 is also an element of R. And then that's it for the 1 node. There's nowhere else that I can end up. So let's go to 2. Obviously, starting at 2, I can end up at 2 because of that self loop. I can also start at 2 and go to 4, so 2, 4 is an element. And those are all the options for node 2. Node 3, I can go from 3 to 1. I can also start at 3 and come back to myself, so 3, 3 is an element. That's it for node 3. And then finally node 4, at node 4 I can go from 4 to 2. And also I can start at 4 and up at 4, so 4, 4 is an element. So this is the relation R. It consists of all these ordered pairs. And this is the relationship as derived from the directed graph. Let's ask ourselves some questions about this relation. We know that relations can have certain properties. One of them is reflexive property. So let's ask ourselves, is this relation R a reflexive relation? So what does it mean to be reflexive? It means that for all x in A, the element x, x has to be in R. So we ask ourselves, is this true? And obviously it is, and we can figure that out by doing things one element at a time. So let's pick an element in A. There we'll pick the element 1. And then look, 1, 1 is an element of R. Similarly, if I pick the element 2, 2, 2 is in R. If I pick the element 3 in A, the element 3, 3 is in R. And if I pick the element 4 in A, the element 4, 4 is in R. So no matter what element I pick from A, we'll call that x, the element x, x is in R. So this is a reflexive relation for the reason we just listed. Okay. What about being symmetric? Is this a symmetric relation? So what do we mean by symmetric? That means for all x and y that I choose from A, when x, y is in R, this implies that y, x is in R. Okay, so how can we work through that? So is this a symmetric relation? So let's look at this. So the way I like to do this is I kind of like to work from the elements of R. So this is for all x and y in A, but what we need is that when x, y is in R, we need this to imply that y, x is in R. So one by one, I just like to work through the elements of R. So let's start with this one. 1, 1. If we think of that as x, y, then y, x is when we flip these coordinates. So if 1, 1 gets flipped, it's still 1, 1, and 1, 1 is in R, and in fact I just circled it. Okay, so this passes the symmetric test. What about the element 1, 3? Again, if we think of this as x, y, when we flip it to y, x, this becomes the element 3, 1. Well, guess what? 3, 1 is an element of R. So this element of R also passes the symmetric test. What about 2, 2? Well, when I flip that, I get 2, 2, and 2, 2 is in R. What about the element 2, 4? When I flip that, I get the element 4, 2, and 4, 2 is in R. What about the element 3, 1? When I flip that, I get the element 1, 3, which is in R. 3, 3 flipped to itself is 3, 3. 4, 2, when I flip that, I get 2, 4, which is in R. And then finally 4, 4, when I flip that, I get 4, 4, which is obviously in R. So for all x and y in A, whenever x comma y is in R, we've just shown by going through every single element that y comma x is in R. So yes, this is a symmetric relation. And then finally, is this a transitive relation? What do we mean by a transitive relation? Well, that means for all x, y, and z in R, x comma y in R and y comma z in R implies x comma z in R. And we talked about this a little bit in the previous example. What this means is that anytime I grab an x, y, and a y, z, whenever these interior coordinates match, the y's match up, that means that the element xz, the outer coordinates, needs to be in R. So again, I like to work through this kind of the same way. Let's pick an element in R. So let's pick 1, 1, and then ask ourselves, are there any other elements in R such that the second coordinate that I just selected, 1, matches the first coordinate of some other element? So the second coordinate here of the thing I've circled is 1. Are there any other elements that start with a 1? And yes, there are. This element right here, 1, 3, starts with a 1. So they match up. So since 1, 1 is in R and 1, 3 is in R, we need 1, 3 to be in R. And look, 1, 3 is in R. I have it circled right now. And are there any other things for the 1, 1, any other things that start with 1? There aren't. So we're basically done with this element. What about the element 1, 3? What other elements in R start with a coordinate of 3? Well, this one does. So now we have 1, 3 is in R, 3, 1 is in R. We need 1, 1 to be in R. And it is. It's right here. Okay. We also have this element starting with 3. So 1, 3 is in R, 3, 3 is in R. We need 1, 3 again to be in R, and I already have it circled. And now we're done with the element 1, 3, since there are no other elements that start with a coordinate of 3. Let's go to the third element, 2, 2. What other elements in R start with a 2? Well, this one starts with a 2 right here, 2, 4. So we have 2, 2 in R, 2, 4 in R. We need 2, 4 to be in R, and it is. I've already circled it. Are there any other elements that start with a 2? There are not, so we're done with this. I do the same thing here, 2, 4. This starts with a 2. So when I match those up, I need the 2, 4 to be in the set R, and it is. We go to 3, 1. 3, 1 can pair up with this. So they match with the interior coordinate of 1, and we need 3, 1 to be an element, and it is. It also matches up with this. So here we have 3, 1 is in R, and 1, 3 is in R. So we need 3, 3 to be in R, and it is. And you just keep going down the list, element by element, finding all the things that it can pair up with. And if you continue in this way, you'll conclude that yes, no matter what x, y in R and y, z in R that I choose, x, z is always in R. So this is a transitive relation.